Now, thinking about acid-base problems. What are the major species in solution? What is the dominant reaction that will take place? Is it equilibrium reaction, or is it essentially going to go to completion? React all major species until you're left with an equilibrium reaction, and you can solve for pH. So there's a lot of things to consider up here when you're thinking about acid-base problems. We're going to start with basically looking at the first two bullets right now. Okay? Looking at what are the major species in solution and what's the dominant reaction taking place in order to figure out things. Thinking about the acid-base problems, you really do have to take into account that the idea that because water is the major species in the solution, water is going to also be a possible reaction that takes place, that self-ionization of water, in terms of who's donating the most protons and controlling the pH. So you have to always think and look back, and this is a very rare question that's been on the AP exam, but it has shown up, where they'll give you, a very weak concentrated, a very weak amount, weak concentration of a strong acid, but you have to realize that that was not going to be controlling the pH. It's actually going to be the self-ionization of water reaction. So we also, when we're going through these problems, we need to take that into account and have that always in the back of our head, looking for that. Most of the time it's not going to be there. It's a very rare occasion when it does pop up. But we need to be looking for the dominant reaction first. Then we can calculate based off of which one's dominating the pH and the concentrations from there. So here, once again, we're looking for the major species. We do know that this one, this is stuff we went over last time, that hydrochloric is a strong acid. It's supposed to completely dissociate or ionize in water. Okay? Completely dissociate. So you get the, HCl plus the water. It's going to make the hydronium and the chloride. So basically, I draw the arrow in this direction because it's supposed to go to completion. It's not really one that reverses a whole lot. Okay? So we're really looking for the major species that will begin this now has dissociated. It has become hydronium and chloride. It's really no longer around. We still have water though. There's plenty of it in the beaker. And we have hydronium now, and we have chloride now. These are going to be what our major species that we're going to be looking at. In this case, the reason why I know this is if I look at the concentration here, this says 10 to the minus 3. And remember, our pH scale is a relative log, it's a logarithmic scale. So something that is 10 to the minus 3 is going to be somewhere in that 3 to 4 pH range. Okay? Something that's 10 to the minus 1 should be like somewhere in the 1 to 2 range, okay? Thinking about that logarithmic scale that we were talking about last time. So I can tell, if I'm looking here, that that's a pretty high concentration, okay? And looking there, that particular case, the hydrochloric acid and its reaction with the water here and creating the hydronium and the chloride is going to be the dominant reaction, and it's going to control the pH. So, as you can see here, highlighting once again the major species because this completely dissociates, and we have a pretty high concentration of it. We know that that would be the dominant reaction there. And our pH, like I said, is going to be in that lower range, and it happens to be 2.7. Now here, once again, this is where, these ones seem, they should be super easy, not a problem. We have nitric here. Nitric's a strong acid. Nitric's going to react with the water. Also going to completion, giving you hydronium and our nitrate as our conjugate over here. So major species. Now I don't really have to consider the self-ionization of water because if I'm looking here, once again, 10 to the minus 2, that's going to be in the lower part of the pH scale. That's going to be down there, and that's going to be driving the pH. Very, very you know, more concentrated amounts there, okay, that I should be looking at and considering. Okay? So then, as we did before, we would just take the negative log of that and get our pH. So as you can see, the major species, once again, because this one pretty much goes to completion because it's strong and completely ionizes or dissociates, we end up having that as well. And our pH is 1.82, definitely driving it. And this is where we need to pay attention, though. Still strong acids, this is that last one, strong acid hydrochloric. But if we're looking here, 10 to the minus 11 is a very small amount of hydrochloric being dumped in. The self-ionization of water reaction, and I'm not sure everybody understood this last time, so I want to make sure we go over this. Okay, we'll produce the hydronium and the hydroxide, right? And it has its own constant. It's the Kw. Concentration of the hydronium is going to be multiplied by the concentration of the hydroxide. And if we are, you know, since if this is pure water, okay, going for the pure here, nothing's dissolved in it or anything, then our pH should be 7, right? Everybody understand that pure water, the pH is 7? Okay, so that means that if it's 7, the concentration of the hydronium should be 1 times 10 to the minus 7. The concentration of the hydroxide should also be 1 times 10 to the minus 7, because Kw is always going to be 1 times 10 to the minus 14. So looking here at our concentrations, this is where I want you to pay attention to that self-ionization of water, is that we end up with this 1 times 10 to the minus 7 concentration that is driving this particular formation of the hydronium. And in comparison to our other concentration of the hydrochloric up here, which one's going to have more impact? Which one's the larger number? This one is 1 times 10 to the minus 7 is a larger number than our 10 to the negative 11, right? So as you can see, the concentration of the hydronium caused by the self-ionization of water would be higher than the concentration that would be caused by the hydrochloric up there. So that's why we know this one is the dominant reaction in this case. And when we know that that's the dominant reaction and it's going to be driving the pH, we would take the negative log of this value, the 1 times 10 to the minus 7, to know that the pH should be right at 7. So just adding a tidbit of acid really, in this case, was basically what's going on here, is they're adding just a tidbit of the hydrochloric. It does not drive down the pH. The pH pretty much stays at 7 because the water is so abundant that it's not really affecting it, and the water self-ionization is keeping it at 7. Okay? Just wanted to reiterate that point because that has shown up on an AP exam where they'll give you this very small little amount of a strong acid and ask you for the pH, and you're like, oh, easy, negative log that, and you get this, you know, pH that's like 13 or something. Well, actually, the pH really should have been at 7. So I don't want anybody to lose a point for that. 7. So in this particular case, because we added very little, very, very little amount of HCl, your pH is still virtually 7. Didn't change a whole lot. Well, because the Kw is 1 times 10 to the minus 14, if we're using pure water that we're dumping this little bit of HCl in, the virtual concentration of both the hydroxide and the hydronium are at 1 times 10 to the minus 7. They're equal. Because remember, pure water should be neutral, should be 7, right? So the hydrogen should be 7, negative 7, so should the hydroxide be negative 7. That's where I'm kind of getting those numbers from, but that's a good question. Yeah. So the pH of this one would be, dominant reaction happens to be your self-ionization of water going on, and water is the major H donor, so that creates pH of 7.